welcome back to the Nerd Burb channel, and in this video I'll be speedrunning an explanation of galvanic cells and voltaic cells, which are the same thing. Okay, so this is a summary if you forgot, and this is everything I'll be explaining later. So in this video, I will use a zinc electrode and a copper electrode, which are the most common examples. But you can apply this to any other element. So what a galvanic cell and voltaic cell has is this. There's a zinc and a zinc ion, copper ion, and copper solid. And there's like a solution of zinc ions and copper ions here, and a salt bridge, which I will explain at the end of the video. Okay, so once you add this together, something crazy happens. Electrons get moved from this side to other side, and using these electrons you can do work by like powering a light bulb or something. Anyways, so why does this happen? And it's because the standard reduction potential of copper is greater than the standard reduction potential of zinc. So what this means is that copper wants to be reduced more, and reduced means gain of electrons. Remember oil rig, okay? So copper wants to be reduced. It's down bad for these electrons. So it's like, give me those electrons, and it becomes solid. And the zinc's like, zinc's weak. And so zinc doesn't really want the electrons. So it actually goes the other way and accepts electrons instead. Because copper's like, give me the electrons. And the zinc's like, oh man, okay, I'll give you the electrons. And so the half reaction is this. So zinc, I like to write out what's happening at each electrode or half cell. So zinc's like, oh, here's my electrons. And then copper's like, give me the electrons. And so copper and the electrons, the copper ion plus 2 electrons, they become copper solid. And for the zinc, it gets zinc, so it gets turned into zinc ion and 2 electrons. And you can see how this makes sense, because 2 electrons is 2 minus charges, and this is 2 plus charge, so these two cancel out the charge. And this is solid, and then the ion is when it's dissolved. Next we have is, so the zinc is oxidized, which means it's losing electrons, and copper is reduced, which means it's gaining electrons. And oxidized side is always called the anode. Reduced side is always called the cathode. And once you add these two equations together, you can see that this is like the net ionic equation of what's happening overall. And from this equation, you can find the mass action potential using these two, because those two are the two aqueous things, but these two are solids, so they're not included in the mass action expression. And you use this in the Nernst equation, which I won't talk about here, but I'll talk about it later in another video. This is also the standard, the cell notation, which is basically the same as this. There's a zinc solid, a zinc ion of 1 molar concentration, copper ion, 1 molar concentration, copper solid. This represents the separation between the two beakers. And then I think this line here is like a phase change, because look, this is solid, this is aqueous solid. Okay, but a super important thing is, how do you find a standard cell potential? Standard cell potential of this. What's the voltage? of these electrons. If you put on a voltmeter here, how you find it is cathode minus anode. So cathode is this thing, and anode is this thing. And you want the standard reduction potential of the cathode and anode. So this would be cathode copper, so it'd be 0.34 minus the anode, so negative 0.76, and you get 1.1 volts. So if you put a voltmeter here, like a multimeter, you attach a multimeter here, you would see this 1.10 volts. Actually, in real life, it'd probably be slightly different. Anyways, another way of thinking about this equation is this. So in this thing, copper, this reaction is the same as this reaction. It goes forward. So that's what happens. So it's the same number as this. But this reaction here, it actually goes backwards. See? Zinc gain electron here, zinc lose electron here. So what I do, so the reaction is going backwards. So the standard reduction potential, the E cell of, just the voltage of this happening is I flip the sign. So it's plus 0.76. And so I just add them together now. So, and I get the same answer. Because what I really did was just I flipped this. And so that's the same as subtracting the anode. Because in the anode, all these reactions go the other way around. Okay, now finally onto the salt bridge. So salt bridge is like a piece of paper or something soaked with some salt. That's like potassium nitrate or NaCl or just anything that's a salt. As long as it's like an aqueous thing. So how do you know which way the ions will flow? Well, you can see like the negative charge is going this way. So without this salt bridge, it won't work because all these negative charges are going this way. And so negative charge is building up here, which will eventually repel the electrons, and the electrons will stop flowing. So you need the salt bridge to balance out the charge. And so look at this. So negative stuff is going here, and the salt bridge, the negative stuff, the nitrate, is going back to the first solution. So now the charges are getting balanced out because it's going in a circle. Like this. So like negative charge going around in a circle. And of course, the positive charge would be going the other way. And okay, here's the summary. You've reached the end of the video. So zinc gives away electrons to copper, which takes electrons. So zinc solid plus so this should be the other way. So the zinc solid gives away there we go. So the zinc gives away 2 electrons, and the copper as substitute electrons to make solid. And then for the salt bridge, the negative charge, you should know the negative charge goes around in a circle to balance everything out, and then the positive charge would go the other way, of course. And so I think that's about it. Thanks for watching. Merry Christmas and a Happy New Year. Okay.